In this video, we shall continue the wave shaping circuits, flipping circuit. Okay, this is part 2. So we shall consider third circuit. In the previous video, we have seen two circuits. In this video, in this circuit, as you can see, so there are two diodes and two reference voltages. So we shall write the equivalent circuit when D1 is on and D2 is off. So as you can see here, this is the equivalent circuit. D1 is being represented by short circuit, D2 is by open circuit. The output voltage, as you can see here, the output voltage is equal to the VR1. So this will occur when the input voltage is greater than VR1. Meaning, so during the positive half cycle, so when the input voltage is positive, I can see this D1 is getting positive voltage on the P side, but on the N side it is already having a voltage of VR1. When the input voltage at the P type of your D1 is less than VR1, so this is reverse bias, and anyhow this D2 is already reverse bias, so this positive voltage to the N side of the D2 is going to further reverse bias this one. So this continues to be there in reverse bias. So during positive half cycle, when the input voltage exceeds VR1, so this diode D1 conducts. That's why it is now represented by short circuit, and the input voltage more than VR1. So we shall see what happens. The condition here is that, so we have the D1 off and D2 is on now. So this is D2 on. So D2 will be turned on only during the negative half cycle, because we have this N type is connected to the supply. So only when the input voltage is negative half cycle, so there is a possibility of this D2 turning on. So this can turn on only when the negative voltage is more negative than this VR2. So that's why this V0 should be less than minus VR2. Then only the diode D2 conducts. The output voltage V0 is given by minus of VR2. Now we shall see what is the condition when both the diodes are off. So there is a possibility that both the diodes can be off. So as you can see here, when both are off, the equivalent circuit looks like this. The output voltage is exactly equal to input voltage. So both the diodes will be off when the input voltage is less than VR1, but it is more than minus VR2. So during that condition, both are off. So that's why we end up with the output voltage is equal to input voltage. And in this particular circuit diagram, so there is no such condition exists, so where both the diodes are on. The transfer characteristics looks like this. As you can see now, so this is the transfer characteristics. We have marked VR1 and VR minus VR2 as the reference voltages. So as you can see now, when the input voltage is more than VR1, so D1 is on and D2 is off. And when the input voltage is in the input voltage negative half cycle, it is more negative than minus VR2. So D1 is off and D2 is on. So when the input voltage is between VR1 and minus VR2, so both are off, the output is following the input here. When the input voltage is more than VR1, the output remains at constant, which is nothing but VR1. So this is what is VR1. If the input voltage is more negative than minus of VR2, the output voltage is again minus VR2. Let us have a look at the waveform. So as you can see now, if the input voltage is less than minus VR1, both the diodes are off, so that's why output follows the input. If the input voltage is more than VR1, the diode is D1 is on, that's why the output voltage is VR1. And again here there is a condition where both are off, that's why output is following the input. So here when the input voltage is more negative than minus VR2, D2 is on, that is this condition, the output voltage is minus VR2. So that's why the output voltage remains at minus VR2. So this way we can find out what is the output voltage and the characteristic, transfer characteristic. We shall proceed now and see the fourth circuit. So here also we have two diodes and two reference voltages. The output voltage is measured across the resistor. So let us write the equivalent circuits considering possibility of one diode on and the other off, and alternatively. And we'll also see, now this is one of the possible uh, condition where the D1 is on and D2 is off, being represented by this. So as you can see now, the output voltage is given by Vin minus VR1. So this input voltage is subtracted by this reference voltage, and we have the output voltage is input minus the reference voltage. So this will happen when the diode conducts. So this diode will conduct only when the input voltage exceeds this reverse bias voltage VR1. So that's why when the input voltage is more than VR1, so this equivalent circuit exists. So let us consider when D2 is on. So this can be on only when the input voltage is in the negative half cycle and it is more negative than this reference voltage, which is of value minus VR2. So that is when input voltage is less than minus VR2. So correspondingly, the output voltage is given by Vin plus VR2, because this polarity of the VR2 will ensure that the output voltage is more than the input by this reference voltage. And here we shall see the third equivalent circuit when both the diodes are off. So since the diodes are connected in the opposite direction, so there is no possibility that both the diodes can be turned on simultaneously, but both can be off, because the reverse voltage that is applied for VR1 and VR2 will ensure that the diodes are off at a particular condition. So that under that condition, the output voltage is 0 volt, and that will occur when the input voltage is less than VR1 and it is more than minus VR2, or minus VR2 is less than or equal to V. So we shall see how does the transfer characteristics looks like. So here also we are identifying the reference voltages VR1 and VR2. So this will help us in drawing the transfer characteristics, because this will help us to identify which diode is on and which one is off. So as we saw in the equivalent circuit, when the input voltage is more than VR1, which is over here, the D1 is on and D2 is off, which is exactly over here. So under such condition, the output voltage is less than the input voltage by VR1. So that is very evident here. This dotted line corresponds to input voltage. So this solid blue line is the output voltage. As you can see now, the output is less than the input by VR1. So this difference is VR1. When the input voltage is negative and it is more negative than minus VR2, this D2 is on. So which ensures the input voltage is more than the output voltage is more than input voltage by VR2. So that is evident here. When the input voltage is less than minus VR2, the output blue line is above the dotted line by VR2. So, but the input voltage between VR1 and minus VR2, it is both the diodes are off. As we can see here, D1 and D2 both are off. The corresponding output voltage is 0. So as we can see now, the output voltage is 0 here. We shall see the waveform how it looks for a sine wave. So this is the waveform. So we'll just have a look at. Now you can see this is of course you can neglect this two lines here. Let us consider when the input voltage is less than VR1, the output voltage is 0. That is this condition. If the input voltage exceeds VR1, the output is less than the input by this VR1. So V in is V0 is V in minus VR1. So that's why this blue solid line is less than the input by VR1. That's why this height is written as VR1. So that continues. If the input voltage further goes less than VR1, the output is 0. So this will be 0 till the input voltage goes further less than minus VR2. So when the input voltage is less than minus VR2, again D2 turns on. That is exactly this condition. The output is more than the input by VR2. That's what is this reference is. So this way we can find out what is the equivalent circuit of the given wave shaping circuit when the diode is on and off, their corresponding output voltages, and we have to carefully write the condition when does this exist, because this will help us in writing the transfer characteristics. Once you are through with the transfer characteristics, you can easily write the output waveform with the help of this reference voltage.